attend tonight, I decided to do a video of material that I want to show you about. So Module 4 is open. This is it in the announcements, and there is a link which will take you right to it. And the changes that I've made are the discussion forum has changed from 2 posts to 1 post, and the due date changed from Saturday till next Tuesday, which of course you know means Wednesday if you decide to take the extra 24 hours. And the discussion is listed here, and then in the discussion directions, you will see that it's the same length as what we're used to doing, but this time it has a question, which one of the 3 approaches, and these approaches are the market report, the forecasting model, and scenario analysis, attracts you the most and why. And when I say attract, I mean you'd want to go and continue to study it. You'd want to learn how to do it in a more detailed fashion. You'd want to actually use it in one form or another. And so that's my first approach. And then the second thing I wanted to make sure everybody understood is that it's a reflection piece. It's your thoughts, it's your ideas. You should assume whoever reads your post, which is mostly me, is quite aware of what's in the chapter. So definitionally, you don't have to go into detail and use up much of your space for that. There are some times where to explain what you're interested in, you would want to, and the reasons you're interested in it, you would want to go into detail. But in general, you should assume that a detailed explanation of what you're talking about in terms of the elements or the factors or the details are not necessary. And I'm also interested in that you make it about from your point of view, and you include your thoughts and comments. So if you look at the rubric, I think that sort of comes through. The subject line is your choice, market report, forecasting model, scenario analysis. The first sentence, I'm asking you to clearly state, this is the approach. You'd be surprised how people sometimes write and they don't want to commit. Well, here's your moment to commit. And then to clearly state or make it clear in your writing from what point of view you're coming at this opinion. Are you talking about as a student who wants to do more research in an area, who wants to learn techniques? Are you talking about it as an employee of an organization who would be the person who does forecast? Or are you talking about it as simply someone who wants to supplement their knowledge in their position as part of the company? Or are you writing about it as someone who would use it to make decisions, and therefore you're choosing the one that's the most useful, either to your professional, to your company, or your hypothetical company, if you want to use it that way? And then state the reasons. Give me the insight into what led you to that, and also explain the reasons. So the differentiation there is pretty small in some ways, but one is a clear statement and the other is the details and the explanation. And I think you'll also notice that there's quite a few points under understanding the required material. While I certainly don't want you to repeat what's in chapter 17 in your post, I do want you to demonstrate that you're using what's in chapter 17 in your post. So you're going to talk about steps of preparing a forecast, then that's fine. You don't have to tell me the forecasts have steps in preparation. You can go right to the step you want to look at, but it should be the ones from the chapter, not some free-floating extra research that you've done. So there's nothing here about extra research. It's really digging into the chapter. And then the other sort of not new, but explanation of what you have required is assignment 2. And it is an assignment. It's not a test. It's a homework. It's a problem set. However you want to go about defining it. It could be a take-home test if you want to go in that direction. Blackboard has no way of me giving it another name. When you open it, it's going to say this test is, or this test has 1 attempt. It means that Blackboard can only accept things where there are questions and answers in Blackboard as a test. And so, yes, that's what it's going to say. And there will be multiple choice, fill in the blank, the short answer questions that we had on, similar to all the three types of questions we had on the first test, but it's an assignment. And the reason you know it's an assignment and not a test is you have a week to do it. You can open it, close it, save it, do as much as you want. There's no time limit on it. It's intended to direct you to sentences and phrases and sections to review chapter 17. So the assignment is, did you get this? Did you see this? This is really interesting stuff. So go back and look at it. And that's what the purpose of it is. So I hope you have no problems getting through it or any, but it will have a slight conditions. One is that you can't submit it more than once and then go back and open it. You have to save it and close it until you're ready to turn it in. Turning it in will be save and submit, and that's one shot. The second one is it's not a group effort. You can use the book as much as you want, and that's what in the chapters posted um, up here, as you may have already noticed. In the when it says readings, there's the chapter, so you can read the PDF file. Um, it turns out that uh, the Stoppard has that website I mentioned in the last section module, and it is open again, but he hasn't gotten to chapter 17 yet. There's no course. There will be a course eventually that includes chapter 17. There will be slides and lecture videos, but they're not there. So we're back to our on our own, and but it's a terrific chapter and full of lots of stuff. As I said in my introduction to it, you you could spend the whole course just doing what's in that chapter. If you did, you still would have to do the other material that we have covered. So I'm not quite sure how one would get it into certainly 8 weeks, let alone possibly 15 weeks. But it would be a kind of iterative process where you would do the idea of what the forecasting looks like and then go back and build the model through the steps that we looked at. All right. So that's the housekeeping. What I'd like to do for the rest of my time, or for a while, is to look at chapter 17. As I said, the PDF file is available. And this is intended to be the end result of having learned about the industry, about the economics, about how it works, about the phraseology, about decision making. And I think if you read through this section, it's unavoidable that the intention is to aid in decision making. And many times when I've taught economics in a MBA program or any other kind of master's program, it's clearly because it's a tool for making decisions. And if you combine that with statistics, you have even more broad, powerful tools to use for making decisions. Now, much of economics and much of the statistics and the approaches that I've used is validating what we believe, coming up with explanations, looking at whether the explanations can be acceptable or sound. And yes, if you want to take that the next step and use that for decision making, you can. But my experience as an economist and a researcher teaching econometrics is someone else has come up with this great theory explanation, and we're going to validate it using statistical methods and actual data that can be found. And that's very different than forecasting. It looks a lot the same, it sounds like the same, it's the foundation for doing forecasting. But I think this chapter is really great because it points out that's only one small approach to it. And it's the biggest difference to me is that I can say, well, we run into a wall, we can stop, we can't go this route. When you're making decisions, you can't do that. and in business, you have to make the decisions. So all of my uptight, prim and proper criticisms of the statistical methods have to be kind of put on the side, but I will talk about them a little bit and try to give you some insight into that in the section on the technical analysis. So, again, I think this is a fantastic chapter in the Stofford's fashion. He gives you an overview quite a bit in the beginning, trying to set it up as forecasting. What are we doing? This idea of unknown, um, trying to get it in context. And he does that very well and does it in a very interesting fashion and kind of puts it in perspective before he gets into detail. So the first section of the um, chapter is clearly an introduction to the overview of what we're trying to do with forecast, when it works, why it doesn't work, that those things are you're aware of them right from the start. And clearly importance of information, and again setting up the whole process of what we're doing. So the three principles, which is what refers to the section that I was asking you to consider in part, in terms of any methodology, is and this I think would be an interesting section to kind of integrate into your thoughts and reflect on in terms of your choice of methodology, are the principles laid out here: relevance, rational, and research. One of the first things I noticed from reading this section in this chapter, which is really great, I don't know whether anybody knows about Edwards Deming, amazing statistician. There's a Deming Prize. He's also often associated with manufacturing optimization and methods. He was part of the post World War II staff that went to Japan and helped them recover from the situation they had created through the war, and made, to a large extent, the methods that Japan had used in their success as a manufacturing firm came from Deming. So one of the things, and I'm a student of Deming, and one of the things that I think is really important in this idea of relevance is, who wants to know what? That's so important. What is the question that you're trying to look for in terms of understanding before you start doing any predictions, before you start um, using your techniques? What is the question that you're trying to address? And then the rationale is, why are you going about it this way? So, first of all, what is it you want to know? What is the problem? And you want to clearly set that out. Then the second one is, what's the rationale for using the approach that you're using, which is also part of what I'm asking you to do in terms of attraction. And the third one is the information that you can find and use going to help reduce the uncertainty? Because that is going to be the biggest issue. If it was all certain, then you wouldn't need to do any methodological approach to trying to figure out what's going to happen. So the next section is talking about the economic model, and it basically refers us back to chapter 4, and tries to give it a little more technical approach by stating these kinds of variables that it's going to include in it. An interesting, uh, from my point of view, use of language is kind of important here. And his approach, yes, I suppose, is sound economics. But it's a business sector economics. It's an industry economics. Not He doesn't have the luxury of being abstract and looking in global concepts. So the first one is tangible, that they're physically verifiable in thus can be used. in my approach, usually they're concepts. They're actually to some extent intangible in the sense that there's not a definite measure. So for the difference, like for instance, and there's something I can show you later, is um, you talk about the he talks about the world economy. Most people have talked about economic growth and the world economy growing and trade. Those phrases are concepts. They're not data series. You have to make a decision on how to measure them. Tangible implies to me that there's some sense that they can actually be measured. The concept of technical is sort of saying that it's by definition going to be defined in a way. So tangible means it's about something from him that can be measured. Technical means that the measure is quite clear by what you're looking for. And then behavioral is actually meaning that it's human characteristics and human influences that are going to be part of what's doing the decision making here. And then wild cards is this idea of there's a certain amount of the world that's unpredictable, and he wants to incorporate that into the understanding of what we're looking at. So I think that's a very interesting approach. I also like his, and this is also where he gets into defining the decision. You really are asking who is the report or the forecasting going to be from what point of view, because that's going to have an influence on how you can manage to do your work in delivering the forecast. So you can look at some of that. I think that's really interesting. And again, these are all really useful and very relevant to the study of maritime and economics and transportation. So I seriously hope you'll all spend some time on looking at that. I have an expertise which I'm going to jump ahead and bring to the discussion so I can spend some time without wasting your time tonight too much. So I need to get down to page 30 here. I'm going to jump to the technical analysis. That's still example. Okay. So under his, once he's established the different methodologies, he talks about using analytical techniques. And opinion surveys, as he clearly states, are broadly used in collecting information. As a matter of fact, um, surveying is become a regular event. It's in terms of trying to measure the output of activities. So if you go to the hospital, there's someone who comes in and does a survey about the food, and there's someone who does the survey about all sorts of things, because the fact that you survived the experience isn't necessarily easy to measure. But if you fill out a survey, then they can use that in their assessment of how well they're doing their job and whether they're satisfying it. And the additional tech, the way he describes it, is this trend analysis and then the mathematical modeling. A couple things I want to say. I think that the trend analysis is very interesting, and it's um, related to an approach of understanding economics, statistical analysis as it stands today. Trend analysis is, to me, related to the idea that there's a whole class of statistical analysis which basically has come to the conclusion that the data series itself is the best forecaster of what it's going to be in the future. That adding additional variables and information is sounds like a good idea, but in many competitions of models, so comparisons of models and having them do their analysis, the ones that were the most successful were ones that were basically based on the history, the patterns of the data itself. And so, what it's talking about in this set of classifications under trend analysis, all of these techniques are relying simply on the data series itself. So, for instance, if you're looking up freight rates for bulk carriers, or you're looking up a oil tanker of a certain type, or especially, and you want to know about freight rates, the most successful prediction of where those prices will be in some either immediately the momentary forecast or the short-term forecast, medium forecast, long forecast, medium to long, you start getting fundamentals coming into play, and they may win out in the situation. But as long as you're in the momentary and short run, you're possibly going to have the best forecast by looking at some analysis of the data series itself. So if you look at what these are in terms of how they're calculated, in this particular one, you're suggesting that there's no change. Whatever has been happening to the variable is going to continue to happen to the variable. Now, there's a couple of ways of looking at that. It doesn't necessarily mean that it's going to stay static at a given value. In many of the cases, it's talking about calculating a trend. How does it change between an average rate of growth or an average rate of change in the variable between 2 points? But that the change that has happened isn't going to change in the future. It's going to be maintained in the future. The other idea is that somehow you have a simple rule of how it's going to work, and that's a little bit, but it's still dependent on the variable itself. The rule is a little more bringing in other information, but it's the values, how it has behaved in the past. The other methods that it's talking about here are all versions of looking at the value itself and using that to calculate the values in the future. I'll come back to that in a little bit. The method that I am most familiar with, and I think is valuable, but as you can see here, it's a small part of how you might go at this problem, is under these categories of mathematical model. Many of you, I hope, have had statistics as an undergraduate and got as far as regression, and that's where we're starting here in terms of the analysis. But that's the dominant approach to what we're looking at. Now, before I go there, I think it's important to point out to you that while this is written as an equation, I think it would be very difficult to find values for the cyclical variable. He does use a method, but in fact, the cyclical variable is looking at the data in such a way that the cycle is incorporated and in many cases smoothed out, but it's not ignored. And I think that's the crucial understanding of what you should be getting here. In terms of estimating a future path for a data series, the trend is basically some sort of average value and how the value changes with time. The cycle and what he uses in his explanation of how you can model the cycle is especially captured here with this seasonal cycle, which is by taking a moving average of the deviations. So what does that mean? It means that the difference between the actual data and the trend, whether you calculate your trend by using a simple take 2 points and come up with a linear path, um, because those 2 points will give you the slope. And then as time increases by 1 unit, the variable that you're trying to capture the measure of is going to increase by a constant amount from period to period. Or to look at something that's some sort of a moving average or a cycle, um, which is it's the data itself. I mean, this is the data. Sorry, this line is created by 2 points in the data. This is created by using multiple points of the data itself and then sort of smoothing it out, finding some sort of average. A moving average means that you just keep taking either 6 months below and 6 months ahead and averaging those out, and then you switch what's included in the average as you move through time. And then what he talks about partly as the seasonal um, cycle measure is how the actual data and this smoothed moving average data differs. And that gives you some sense of the cycle in terms of seasonality. But in all the three cases that he discussed here, and going further in this section, the only data that you're included is time and the series you're looking at. And in fact, in some of these analysis that he's going to talk about, these auto regressive processes, they do include time, but they work provided where you are in time is not the crucial point. It's how far away from this given point you are in the calculation. So in the explanation of what you're looking at, it's for it to be a successful approach, it can't be that it's the 1960 January data that matters. It's that there is a pattern that when you take a point and you look at what it's like a year from now or 2 years from now or 3 years from now, that it doesn't matter where you start and then go forward, the pattern is existing and you're capturing some sort of form of that pattern. And that's a nature that has an important consequence for the methodology. If you can't do that, then the methodology is going to be not the appropriate method for you to use in this particular case, or in the other form. So I wanted to do regression analysis for you for a few minutes. The two things that we have here is the actual data. So in a regression in regression analysis, and it looks like there's two pieces of data and that's all that matters. But let me go down here because this is the more powerful approach. It's a specific form of calculation. This is the one. A specific form of regression analysis. It's ordinary least squares regression. That's the methodology. The idea of modeling a data series in a linear combination of another data series and some random component is regression modeling. Ordinary least squares is a specific method of estimating a regression. But to understand a lot about what's going on, this chart is excellent. There's two variables here, but the straight line is just the average value of the variable measured on the vertical axis. In statistical analysis and bringing up regression in ordinary least squares, the premise is that you're going to conduct a random experiment. And you don't know, you're uncertain about what the value of y will be as the outcome of that experiment. And you are asked to come up with a guess, an estimate of what the value will be when I randomly select from the population one element, which will have a value in that from the population. What will you guess is the value? And this straight line says you're going to guess that it's the expected value, it's the average value. In if statistical analysis is based on probability, if you say that this is a random variable, means that you're saying it has a range of possible values that can occur and probabilities or frequencies in the population associated with that range of possible values. So each value has a frequency in which it occurs in the population. It has a frequency or probability that when you conduct the random experiment of selecting one element from the population, it's going to have that value. And your job is to predict what that value is going to be when you conduct the experiment. Well, most people who get involved in the statistical approach would possibly say then it's the average value. On average, it's the mean value. Now, the mean value is saying a little bit more than on average. It's saying that it's the weighted value of the possible values in the population, and the weights are the probability that they would occur or the frequency at which they occur in the population, depending on your where you are in your analysis. So what this straight line implies is that you could have predicted the value of the price of ships in terms of millions of dollars, and it didn't matter what the age of it is. This value is the average age of the price of ships. So you would have all the possible values, and frankly, age is not even considered. It is a characteristic of the population of values, but it's not being captured. We're really just saying of all the ships that we're looking at that have prices, this is the average price. So if I'm going to randomly select one ship from a population and I know what the average price is of those ships, why not just predict that it's going to be that average? Because what else am I going to predict? The idea of a linear regression is that there may be knowing additional information that will help you improve your prediction. And that additional information in this case is the age of the ship. So if I can isolate the age of the ship and then say, the ship is going to be 10 years old, and I'm going to randomly select from the group of ships that are 10 years old, so the subset of the population that fit that category, what would you predict the value is going to be? And that's where we start to be able to get additional information in terms of our relationship between the dependent variable, the price, and this age of ships. And so, in fact, what we have is that the line that's called a regression line is the expected value of conducting this experiment over and over again at every age that's possible. So that this line is in itself an average, but it's an average which depends on the value that the ship has of age. So I have all these possible values. I'm predicting the value of the ship on average, the expected value, given that it's 10 years old or given that it's 15 years old. And if I put that information together, I'll be able to form a line. So YC is the value we're going to calculate by using a linear relationship between the dependent variable price and the independent variable, in this case, the age. If I conduct that using a range of values for X, and one of the things that's important in being able to use this method is that there has to be variation in this variable that I'm going to say is part of my prediction. Because what you're If the price of ships was constant all the time, then just using the expected value would be fine. But if you believe that it differs depending on the age and you want to take that into account, then you have to hold everything else constant, and you're going to establish some sort of a linear relationship here. And you're trying to use the variable age to explain why the price isn't the same all the time. And so you're looking at the difference between the average, which is sort of your best case, your benchmark, and the average for the group that fits under whatever this age would be, which is like maybe 10 and a half, 12, 11 years. And then you're looking at the difference between the Y and what you guessed and Y and what it actually is at that point in your data set. So you're trying to calculate how the data varies, meaning the prices vary, using the additional information of the age. And to be able to do that, the best approach is to minimize the distance between the actual value and your estimated value. So what you're trying to do with ordinary least squared is on average have the smallest distance between your line and the points. But how you measure that is by looking at how much of that distance makes up the distance between the actual value and the average. So one of the ways to think about it is that what you're doing with the regression is saying, well, if this is the actual and I had gone with the expected value, I would have been off by that much. How much closer, how much could I reduce this distance by using a linear regression that relates the age to the price? And this shows that if I had taken that into account, I would have had at least part of this distance explained by the calculation. I still would have been off by a certain amount. But if on average this part that I'm off still is minimized, then my regression line is going to become a good fit in terms of better than the average for my calculation. And in fact, the printout that you have here, a lot of it is about measuring how well you did based on that distance. And in the section which he refers to as analysis of variance, he talks about the relationship between YC, as I was talking about, and he's trying to show that if you minimize the distance, it will be shown up by having a smaller standard error, which is given in every regression in two places. One is the sum of square residuals. So this is sort of the average distance between all your data points and your line. But for a specific coefficient, you can say that the standard deviation in the terms of the range of possible values you would get for your coefficient and the estimate and the distribution that you have, the expected value, is measured by this standard error. So what you're looking for when you run a regression are a couple things. This is a way of using those measures I showed you in the graph, but for your whole data set, for your whole calculation of your regression line. Remember, I said you wanted to have the average of the distance between your estimate and the true value. You wanted that to be as small as possible on average. We square it to exaggerate it, so we take a high value for being off by this much and a really small value by being off by this much. So we average that out, um, and we sum it up, and we get the measure of that in this expression here, which is the sum of squared residuals. So the average distance of what we're doing in terms of being off or different between the regression and the actual values on average for the whole line and data set is captured by this number. Now, this number is going to be related to the actual data set you have. So you often want to use data that's standardized, that's comparable. So the R squared that we have here is saying that this is the sum of squares how much we explained. This is what we didn't explain, and this is what we wouldn't have explained if we had used the expected value as the estimate. So let me show you again using the graph. The total sum of squares is the average. You take each of the observations, you calculate the value of the actual value minus the mean, you square that value, and you add those all up. And that gives you the total sum of squares. The residual regression sum of squares is taking the distance between the regression line and the actual values. So you take your actual value, subtract the residual line, you square that, and then you sum that up across all the possible values. And what you're interested in is how much of the off you would have been are you able to explain by using the regression? How much is it better? And that's one of the problems here. Better than what? If you didn't have the baseline benchmark of the mean, you would have a hard time saying that this is a good estimation. But this gives you a benchmark from which you can say, I've done better than this. And the R squared I was showing you is in fact the proportion of this difference between the average and the actual values and how much you actually explain using your regression. So the sum of squares of the regression divided by the total sum of squares is going to give you what percentage on average you're calculating by using your regression. So of the variation that you would have and how much off you would have been if you had used the expected value, you're explaining that by using age as an additional variable by 90%. So you've done quite a good estimation. And the small sum of squared residuals is saying that you've left out a small amount. So this method is a really useful tool for explaining how your regression is going, but I assume I've sufficiently showed you that it's not a simple one if you haven't done it recently. Anybody can run a regression because you can do it in Excel. Anybody can run a regression as long as you have two data series, whether they're related or not. You'll get a printout that looks something like this, and you should be good at interpreting it if you're going to use this approach. And as you're going to be a consumer of reports, you also need to be able to read these kind of reports. One of the big issues that I need to put into your head before I leave tonight is that there are certain assumptions about the data that have to be made for this regression to be even legitimate as a methodology. The irony of time series is that you can't be certain whether they move together because there is a fundamental relationship, which is what you're relying on, or if they both move on a random pattern and just for this period of time, the random pattern matches up. And if that is the case, then your results are what they call spurious. They're not legitimate results. And there are many techniques, there are techniques to try to test that. And it's difficult because in most real world data, you're looking at time series. And when you run against the idea that you can't use it in this simple model of estimation, because what you're getting is, yes, it's a pattern, but it's not a causal. Well, it's never going to be causal, but it's a simple event that happened because it's not going to happen again. That it's random that it happened this time, I guess is the best way to say it. And so you should always be somewhat concerned when someone brings you regressions for time series and they haven't even looked at the legitimacy of using a regression analysis for that time series. Just one other note, that if you are legitimate in using it and you restrict it to only one variable instead of the multivariable models that he goes into later on in the next section, then you also have a feedback effect, which means that if this second variable is a significant explainer of y, and you've left it out of the model, then what you're picking up on this coefficient may actually be compounded, not the effect of just x on y, but what you've left out of the equation. And so statements that you make will be incorrect because it's implying that what you're measuring here is just the impact of x on y. But when you leave out the second variable and you look at estimates for B1 here, you're going to have what's called bias in omitted variable bias, which means that if these two variables that are at all correlated, then what you're picking up in B1 is not only the impact of X1 on Y, but also some indirect approach of X2 on X1 and then through that on Y. So I'm also skeptical when people drop variables if they don't have a good reason for doing it, and not that statistically significant is a good reason. It sounds like it should be, but if you rationally believe that this is an influential and you're leaving it out, then you may be biasing the variable who you've left in terms of its measure of the influence by the coefficient, and you have to take that into account. Okay, it's 10 o'clock. I'm going to stop now. And if anybody's interested in hearing a little bit more about this, I'll talk a little more about it next Wednesday night. Okay. Good night.